As an extension of the correlation analysis, we can use a regression analysis to make the correlation result more useful. More useful means that we can produce an equation that quantifies the relationship between the cause and effect. Whereas the correlation analysis only investigates the relationship between the two variables. The regression analysis can produce an equation as really a product of a research. Differently from the correlation analysis, the regression analysis expects the cause and effect. And it's you who assigns the variables with each role. In this video, we learn about the simple regression analysis. When there is one cause, we call it as simple regression analysis, or more simply, regression analysis. When there are more than one cause, we need to perform a multiple regression analysis that will be covered in next week. So when do we need to conduct a simple regression analysis? It is used to address how well one independent variable, so one cause, is able to predict a dependent variable. That's a result or the particular outcome. So typically, we put the cause on x-axis and we put the outcome on y-axis. If you remember the relationship between donut and fat, in fact, you can define any of the two as the cause or the effect. Here, the cause is donut intake, and as a result, we assume that the person would gain the weight. And here, we considered gaining the weight as the cause. So consequently, the person might have more appetite, so may eat more donuts as the result. So either model is possible. And in either case, we can try the regression analysis. I personally think the left chart looks more interesting because this one is too obvious. And both charts are scatter plots, and the regression line is overlaid to show you the trend of the data dispersion. Fortunately, this scatter plot seems to have no outliers. Also, the data are more dense when they are closer to the regression line. So, more dense closer to the dense line, and the more sparse when they are away from the regression line. Therefore, the data are adequate for the regression analysis. Then let's get the equation of this regression line. In Excel, it is called as a trend line, and in some documents, it is also called as a fitted line. A regression line is fitting to the data by minimizing the residuals. Residuals are in Korean language, 잔차. And the residuals are calculated by the sum of square errors. Therefore, the regression line should be the one that best fits to the density trend of the data. the residual is the size of error. Regarding a certain x value, let's say 20, so-called ideally, the y value should be on the regression line here. If it is so, then the size of residual is 0. As you learned many years ago, a linear function has a form of y equals to a multiplied by x plus b. In statistics, the beta is more frequently used to refer the coefficient. The equation of the regression analysis can be named as a model that proposes a trend of certain phenomena or observations. Therefore, in some research, the equation as such is a good outcome. So let's learn more about the method to obtain the alpha and beta values. Firstly, the beta indicates the degree of inclination, the degree of slope. This inclination is supposed to be the best fitting slope, best fitting to explain the entire data. And the beta is calculated through by dividing the covariance of x and y through the variance of x. And this line definitely passes through the mean value of x and the mean value of y. So this line passes through the x, y, and the x is the mean x and the y is mean y. Therefore, we know the slope and at least the one point where this regression line passes through. Based on these two information, we can calculate the intercept. In Korean, we call it 절편. By the way, this covariance reminds us of the R, and R is the coefficient of the Pearson correlation analysis. And the R is obtained by dividing the covariance, but through the standard deviation of x and the standard deviation of y. Because the variance is a square of standard deviation, the beta is also expressed as R multiplied by standard deviation of y, standard deviation of x, right? So knowing the R value and SDX and SDY, we can also calculate the beta value. So eventually you have the slope and intercept data, and you're finished with the equation. Then we need to know the size of determinant coefficients. The R square denotes the determinant coefficients. The R square indicates how strong the regression line is fitting. That is, the R square in percentage unit of the data is explainable or predictable by the regression equation. And the rest, which is 1 minus R square percentage, are considered as errors. And therefore, the R square varies between 0 and 1. The R square is the ratio of variance of y values on the regression line. So perhaps somewhere here can be the mean y. So the variance of y value on the regression line means, for instance, regarding this x, the y r should be here, because according to the regression equation, the y value should have been here, but the actual data has the y value of this. Therefore, when the actual y values are closer to the regression line, the denominator will be closer to the numerator. On the contrary, when the actual y values are far away from the regression line, the denominator will be bigger. Consequently, the r-square value will be smaller than. In fact, when the r-square value is smaller, it indicates that the equation has less ability to explain the data spread. Also, it equals to the square of correlation coefficient r. When the correlation coefficient between two variables have been, let's say, 0.7, which is considered as quite large size of strength, but the regression line actually barely explains the half of the data, because you get 0.49 by squaring the 0.7. And when the correlation coefficient is 0.7, then you can estimate that, well, you can draw a regression line, and that regression line will have an ability to explain almost the half. So 49% is almost equal to 50%. So its ability of explaining the 50% of the data spread. Then let's consider an example. We have seen this chart already. In this chart, the x-axis stands for the lightness of a color, which varies between 0 and 100. And the y-axis is the bitterness value. Based on this scatter plot, let's get a regression line that is in straight shape. Okay, I copied the data in Excel sheet, and I will show you a wonderful function of Excel. So simply you draw this scatter plot, and I used the data set of these two columns, and you click the data, the plots, and click on your right button and add trend line. So here we can display the equation on chart, and we can display the r-square value on chart as well. So let's see it bigger. So we have the equation of this regression line, which is this, and the r-square value is a result like that. Therefore, based on this result, we can conclude that this trend line or this regression line has the ability of explaining of 64%, approximately 64% of the data spread. In addition, we of course can perform regression analysis in Excel by clicking data analysis and regression input x range, x is lightness. Let's create here lightness label, and in y range bitter. Okay, and the output range starts from here. Okay, right. So let me briefly explain you what these results are explaining or indicating. Firstly, the ANOVA test is here, and this ANOVA test is testing whether this regression model is statistically significant. And we can convert this into more familiar expression. Okay, so it's smaller than 0.0005, right? It's smaller than that. Okay, so this regression model is statistically significant. That's what we can get from this information. And for that, the ANOVA is applied. And then this table presents us the coefficients of this formula. And let's reduce the decimal points to 3. Okay, so here L is the lightness here, and intercept is actually the alpha, and which is identical with this, right? So this value is here. So based on this table, we can write like y equals, or bitterness equals to the coefficient for the lightness is minus 0.027 multiplied by lightness, and then intercept, this is a plus positive value, plus 3.862, and then this explains r square is 0.636. Yes. So r square value, I got this from here. Okay, and we can use this table to create this equation, and we already have checked that this equation is statistically significant. In addition, because the data dispersion seems to be more fitting to this kind of a curve line, so let's try to simply try out different trend lines. Exponential, we can compare the r square value whenever we click different trend line shape. In exponential one, it was similar to this, and well, this is not the one I expected, so I think the power one, yeah, by power one we have obtained the r square value of, yeah, to almost 72%, which has a with noticeable increase from this. And then let's see in what formula this equation can be expressed. You see here, although we have obtained more increase in R square value, the equation became more complicated. So here you need to negotiate whether you take the increase of R square value or you choose a more simpler one. And let's try the regression analysis in SPSS. We have the same data set and the analysis, regression analysis, and then linear as the cause. So the cause, so independent variable here, and dependent variable, the bitterness. Okay. Here we have same R square value, and the ANOVA test results the statistical significance. So the model is statistically significant, and the coefficients, the intercept or constant is this value, and the inclination or the slope is minus 0.027, which is identical, which should be identical to the Excel results. Then let's try out a curved shape. So we take independent variable of lightness and bitterness as dependent variable, and here actually you can get the linear model as well. So when you are very fluent in SPSS, then probably you will straightly using this function, because this also includes the linear model anyway. And you click the thing you would take in case you have very high R square model. But the data set are in this case relatively simple. So in my case, I wouldn't take these two because they are not really fitting to my simple research structure. So I just try out different things. Because SPSS does all this complicated work for me in a few seconds. So why not? Yeah, so these lines are corresponding to the shape which I selectively clicked, and here presents the R square value, and you can take, theoretically you can take the largest one, but overall all seems to be quite similar to each other. But the first one is linear model, and from the second one it becomes either complex or not necessarily complicated. So after having compared 6 different models, and all 6 are statistically significant, so it's me who can choose one of these 6 models, and as far as I have enough rationale, it's good enough. And I personally would take the linear model, because although it has a less smaller size of R square, but the difference between the other models is relatively small, and it's much more simple than the other ones. So I would take the linear model.